Okay, I think I'm live. I'll just check the audio and then we'll start. Okay, I'm gonna change the audio just a little. It's already at full volume. Maybe I need to speak louder, but that's fine. Yeah, let's get started. So for today, I think one lead code question and then I want to build one project. I'll start with building a Miro board for it so that everyone can see what I'm building. It's a stupid thing, but I really wanna, or at least I really need to do it. I will share what it is once I solve a few questions. A couple of us at most. Maximum product of three elements after one replacement. You are given an integer array nums. You must replace exactly one element in the array with any integer value in range 10 to the power minus 10 to the power 5 to 10 to the power 5 inclusive. Performing a single replacement determine the maximum possible product of any three elements at distinct indices modified array. Return an integer denoting maximum product achievable. Okay, sure. And that seems like a very easy question. So you're given an array with n elements, but you kind of only care about the ones whose ABS X is highest and second highest. I think those are the only two you care about. And assuming the array will always have more than two elements, I think that has to be a given. So given this, you just get the highest and second highest element in terms of absolute distance, and then multiply their product with 10 to the power 5. Yeah, I think that's it. Worst case, the answer would be 0. Yeah, like here. Answer can never be negative because we get to choose whatever we want to do. Okay, so here's what I'm thinking. I just need the maximum element, max of array. Uh, so not maximum, I guess max of absolute of array. And the second max, I don't know how I'm gonna find the second max yet. ABS, ARR. And we multiply these two and then we multiply it by 10 to the power 5. That's it. That's all we need to do. And I think it satisfies. So in this case, for example, the answer would be 12 into 10 to the power 5. In this case, it would be 35 into 10 to the power 5. Sure. The fastest thing that I think we can do is just sort them if I'm not wrong, and we'll just no. Okay, so we just do absolute. Still, there's no function for second highest in Python, so either you run an entire. I'll tell you exactly what I mean. Visual Studio Code, and I need to change the question number as well. LeetCode. Sorry, what was the question number? 3732. Group properties 3732. Okay, and VS Code. Let's full screen. 3732. Why is it not saving the thing? DSA by 2. Okay. Uh, I believe numbers can be same if I'm not wrong. Yeah, there's no condition K, all are distinct numbers. So what we need is hmm, what we need is somehow to find the highest and second highest number. Sure. First thing I'll do is max is uh, highest is equals to max nums, and no, actually not max nums, APSI for IE. But then again, this would give us the negative number. Okay, honestly, I think the fastest way to do this is just to sort it. So num start sort actually new nums is equals to, but it's worse complexity. I should do it correctly. Sure. Highest is equals to 0. Second highest is equals to 0 for num in nums. If ABS num is greater than highest, second highest becomes highest, and highest becomes ABS num. Again, we are just eliminating positive or negative because let's say both are negative. I'll show you here. Let's say the first number is minus 10 to the power 4, the second number is 10 to the power 3. Irrespective of this is minus or plus, we can just decide whether we want minus 10 to the power 5 or 10 to the power 5. Basically, uh, whatever the product is, if it is negative, then we add another negative. If it is positive, then we simply add a positive, uh, or multiply it with positive 10 to the power 5. So it does not matter whatever we choose. LF, ABS, num. I don't think there's a faster way to write this in Python. So just write it like this. Second highest is ABS, num. That's it. We get highest and second highest. So we just do return highest, star, second highest, star, star, five. Let me quickly copy it and run it. I am now realizing you guys cannot see this. But I think you can see the run of it. I have just pasted the code here. Maybe I should hide it, but I'll just submit it and this like it takes care of the zeros automatically because worst case one of them becomes 0, which is fine. Or sorry, they'll stay at 0 because they're already at 0 and just comparing greater. Okay, this was easy. I'm happy. Let's solve another one and then maybe we'll move on to project. I don't know why this button doesn't move. I want to do an easy question. Hard, sure, we'll do hard. A game on an undirected. Let me change 913. Let me change this. Music is too loud. Is it too loud in stream as well? I hope not. I'll lower my volume for me a little. And I will increase its volume for you guys so that you guys can continue to hear it. Yeah, I think my voice is good enough for this. Okay. Let's switch to the next question. First 913. Let me quickly edit this. Okay, okay. Mm, yeah, let's get started. A game on an undirected graph is played by two players, mouse and cat, who alternate turns. The graph is given as follows. Graph A is the list of all nodes B such that AB is I forget what it was called. There were two ways to store a graph. I just used them. I forget the name of the way this is stored, but sure. Uh, the mouse starts at node 1 and goes first. The cat starts at node 2 and goes second, and there's a hole at node 0. Okay. During each player's turn, they must travel along edge of the graph where they are, for example, if mouse is at node 1, must travel to and sure. Additionally, it is not allowed for the cat to travel to whole node 0. Sure. Then the game can end in three ways. If cat ever occupies the same node as mouse, cat wins. If ever the mouse reaches the whole, mouse wins. If ever a position is repeated, that is, the players are in the same position as a previous run, and it is the same player's turn to move, the game is draw. Given a graph, assuming both players play optimally, return 1 if mouse wins the game, 2 if cat wins the game, 0 if the game is a draw. Okay, this looks like a very interesting question. I like it. So here's what we are given. We are given a random graph. This is like one of those games that we see on in ads where you need to, like one of those games basically where you need to go from A to B, your partner goes from A to B, and you capture their partners. Yeah. Anyways, let's focus. To solve this, the first thing that I'm thinking is, what does optimal play look like? Because that is kind of the only problem, right? So if the mouse is here, if the cat is here, and if the hole is here, let's say this is the 0 1, it would take 2 turns for the mouse to go here. So the cat, oh sorry, let's actually add another node here. Yeah, if the mouse is here, if the cat is here, and if this was the, then playing optimally would mean that the cat would go here in its first turn, and it is able to trap the mouse. Basically, no matter where the mouse moves, the cat always catches it. Uh, sure. And in a turn, all of them move, if I'm not correct. During each player's turn, they must travel along. Oh, okay. For example, if mouse, it must travel to additionally. If, uh, the mouse starts and goes first. Okay, so it's a turn-based game, which means in the first turn, the mouse moves here, then cat goes here, then mouse moves here, and cat goes here, and it is captured here. Okay, makes sense, makes sense. Now, how do I solve this? So, first things first, let's check the constraints. So the graph length is not more than 50. Okay, okay. Mouse and cat can always move. Okay, this is given that mouse and cat can always move, meaning graph ij is not equals to I. Sure. Graph dot length, which means it can reach to 0 to in minus 1, and at least one node is connected to the graph. Okay. Okay, makes sense. Now, what would be the optimal way to solve it? See, one thing that I'm kind of wondering is it always beneficial for the mouse to take the shortest path to the hole to kind of try to win the game? Is it possible that the mouse does not take the shortest path and still wins the game? For example, right here. Yeah, it definitely is. So right here, the mouse, and then we can do this. There's no such rule that cycles aren't allowed in fact, cycles are allowed in the first voice itself. In here, like this takes the mouse 3 steps to reach the hole, and this takes the mouse 4 steps to reach the hole. But again, if the mouse takes the shortest path, it loses because the cat captures it. Otherwise, if it takes the longest route, then it reaches its goal. What if it was something like this? Now the cat can jump to here in 3 moves, but the mouse still escapes. In the third move, the mouse would be here, and then the fourth move, it would reach this place. Okay. So what I'm thinking is just running a brute force, calculating every possible solution, whose turn it is, and seeing whether the cat or the mouse can win from that position. Uh, what I mean is, I think it's called like complete. So what we'll do is we'll start here. We'll kind of simulate the entire game for every possible move. From here, if the mouse goes here and the cat goes here, if the mouse comes back and the cat goes here, these are all separate events, and in each event, what happens. Or one thing that we can do is, but like, okay, so what is the total number of, yeah, so then the thing becomes, if we do this, if we do the brute force approach where we are looking at every possible outcome, then the simple question is how many possible outcomes are there? So it says that there are 50 nodes at most, and in each node, either mouse or cat can be there. So we will have like 15 to 49 total ways their placements can be, and then another into 2 for whose turn it is. So for example, this is one possible orientation where mouse is to go first, and then there can be an orientation where cat moves in this particular round first. So can we make that happen? 1, 2, 3, 4. So it takes the most 4 moves. Let's actually simplify it so we know we can make it happen. Yeah, so mouse takes 3 moves to go here, cat takes 2 moves to come back, which means there will be a position where cat goes first. And in that case, yes, this is the total number of possibilities, which is not a lot. Now, how do you calculate? We just see if a particular possibility is already available. If it is not, then we just check for its subsequent possibilities. Basically, we run the simulation once and see if if this was one of the possibilities that we had already seen, and what was the outcome. And then we return whoever's move it is based on that. So if it is the mouse's move, we return if there's a possibility for mouse victory, or if not, then we return draw if that was a possibility. And if that wasn't the case either, if the cat wins for sure, then we have to return cat. We cannot do anything. Sure, makes sense. So more form, I'll explain whatever I was thinking more formally. No matter what the graph is, one thing that we will do is simply assume that, or basically we'll do the brute force approach where we'll try to calculate the answer for all possibilities. So let's say the mouse started here and the cat started here, and this was the 0. We'll basically start simulating the game ahead. So let's say in the first turn, the mouse goes here and this becomes our new move. So for this particular case, the simple, what to call it, like the key or the unique key defining this case would be, let's say this was 1, 2, 3, 4, 5, 6. So we'll do mouse's position, cat's position, and who is to move. So 3, 6, and cat is to move. So let's say 1. And if our mouse were to move, then we'll say 0. So let's call it cat move. Yeah, 1. And then this is M pause, C pause, and this becomes cat move. Or actually, since we are like starting with mouse move, so we'll send 0, and this will be called M move. Whose turn it is to move. So if it is mouse's turn, then it would be 1, otherwise it would be 0. This defines a state of the game, a possible state. Similarly, we can have another state, 361. Let's say the mouse came here and it was the cat's turn. Oh, sorry, mouse's turn. And we keep on simulating this game. Total number of simulations possible is there can be any number in here, there can be any number from 0 to 50. So 50 times 50 times this can be 0 or 1. So 2. So that's not a lot, that's just 500 possible cases. Which kind of makes me wonder that this becomes an easy question if you can just brute force it, and since the graph's length is just 50. And see, the thing is, no matter how many nodes this thing is connected to, it's not going to increase the complexity by anything. Number of edges don't determine the complexity, because again, we are storing an entire state and the number of states is limited. It doesn't matter. So for example, let's say there was an edge here and you had already calculated this state. If the mouse is here and the cat is here, then the mouse wins. No matter where the cat moves, mouse will always win because it can reach 0. Given this, from here, the mouse goes here, and again, no matter whose turn it is, we know that the mouse will win here from here for sure. Same thing goes here. No, so wait. Okay, I'm confused a little. No, yeah, that still works, right? So if the mouse was here, let's say, not here, let's say there's another node here, and this is where the mouse was. Let's call it 7. Now, it takes the mouse 2 turns to reach this, it takes the cat 3 turns to reach it. Sorry, then I'll actually connect this to this. Now it takes the mouse 3 turns, it takes the cat 3 turns. Now, for this particular case, if the mouse was here, cat was here, then the mouse always wins. So no matter whose turn. Okay, so the turn is the kind of only thing that flips. It's not how many turns have passed, it's not anything else. Yeah, then this thing still holds, that it only depends on this many, or there can be at most this many unique number of cases. And it won't take us a lot of time to figure out each of them, because again, to figure out one case, we just have to figure out all the cases in its surrounding. Worst case, we just figure out, is it possible to ever be stuck in an infinite loop? So let's say I was trying to figure out a case for 6, 1, 6, 0, or 1, let's say, mouse's movement. So what would the ideal gameplay look like? The mouse simply goes to 0, right? Given this, we can say with certainty for the answer for this is what, 1, when mouse wins. Yeah. Now, what about a place like this? How do we calculate? Has something like this been already calculated? If it has, then okay, sure, that makes sense. So to calculate for this state, all you do is you figure out whether the answer for any of its neighbor states is available. If it is, then you continue. Or basically, you know what the answer for it is going to be. The only problem I have is, how do you figure out, like, basically, kind of the only thing I'm wondering about is it possible for us to never be able to even figure out where to begin with? And in that case, I would just store the answer. Like, for example, in this case, anything around 0 simply becomes like 1, as long as the cat is, it's not cat's move and it is not 1 away from the mouse. So those are some cases that I can figure out, like statically, or basically by just brute forcing right away. I don't think I should do that. I think I'm just confusing myself. Let's see. This was the case, and we were trying to figure out what the answer for it is going to be. So the thing is, Either we do, hey, is there a zero available? If it is not, if it is, then we just set the answer for this particular case. Mm, Similarly, when we are on cat's movement, then we figure out, hey, is the mouse available in any of these positions? If it is, then we figure out the answer for that particular case. If it is not, then we stimulate it, simulate it further once. So if the mouse was not here, but here, let's say, then, and it was mouse's movement, mouse's turn. So 361. This is our state. What we do is we try to figure out 260 and we try to figure out 160 and we try to figure out 460. Mouse move. So we need answer for these three cases. 260, again we try to figure this out. This gives us again no, this gives us 3 2 1, or no, that's the only thing it can give us because mouse and cat have to move in their turn. I think that's a requirement of the game. The mouse starts at the hole during it. They must travel along there, so they have to move somewhere. That is the only possibility for 3 to 1. And then 3 to 1, again, we try to figure out what the answer for 3 to 1 is going to be. That is either 1 to 0, 3 to 0 gives us basically like the mouse moves to where the cat is. So this I think already clears out to be 1, which we don't want in case of mouse. So we would simply eliminate that one. Mm, Sorry, not 3 to 1. I have oh, this is 5. This should be 5 to 1, not 3 to. Sorry. This should be 251, not 3 to 1. Then we have 150, or we have 350. I'm just wondering whether it would run in an infinite loop, like, or will we actually figure out the answer. So the reason why I'm not worried is how do we figure out? Okay, so we need to keep in check how, like, what things we are still evaluating. And if we have evaluate, like if we are already about to, like going to evaluate a particular condition, let's say we arrive at 160 again somehow, for example, after this one, when the cat moves, it goes back to 6. So I don't know if you guys can see this, so I'll try to bring it here. A possible outcome after this is, a possible state after this is 161. Mouse is here, cat is here, and it's the mouse's turn, and then we can simply, and then the mouse can simply bring it. Okay, okay. Okay, I think we should start coding it. I'm pretty sure my solution would work. I'm just a little confused. Basically, I'm just a little worried whether this is the optimal way to do it or not. But I think that's fine. So I will actually start coding it because I'm taking a lot of time. Let's see, 9 3. Okay, let's get started. So first things first, we need to maintain states, which should be a dictionary that also solves, and then calculating states. Sure. So we have, uh, let's call it DP because it's just easier to call it DP. And then we'll have calculating states, or states in progress. I'll just call it calculating. This will be a set. Uh, okay, makes sense. So in calculating, we'll store the ones that we will calculate soon, and in DP, we'll simply store the ones that we have already calculated. And this should ideally just give us an answer. Uh, what I'm kind of wondering about is it possible that we discard a state? No, so we calculate everything about that state before. Huh. So one thing that I was wondering about is what happens if, let's say, this state kind of gives an answer later than this state, but that's not possible. Again, we will do recursion. I think that's the best way to do this. We will recur over all possible states, and to do that, another thing that we can do is we can just run through all the states and it would tell us uh, simpler ones. So let's say something like 320. This is a simple state because the cat would, oh sorry, the cat would simply go from 2 to 3 and the cat wins in this game, in this war. And these are easy to calculate. We just loop through all of these and we see, hey, is the mouse close to 0? Can the mouse reach 0? Basically, if it can, then we are golden. If it cannot, well, then we might be having some problems. Mm, just this class. Oh, okay. Sure. Let's see. Then the mouse, and then this kind of helps us a lot because we will have some answers to some states beforehand, which speeds up the process. Because let's say for example, if we were to calculate for something like 211, then we know that mouse wins, but we would never try to calculate this one or this one. Basically, we'd eliminate some of the most ridiculous calculations. The question then becomes is why not just continue doing this? So what I mean is, why not just say, hey, we have like if we have answer for this one 211, then what's stopping us from getting the answer from 311 either? No, not from 311, like from 531 either, because then again the first move becomes that. So we just keep doing this until we have an answer for all possible states. Basically building up our answer, but then it's not guaranteed to include our any original test case. Sure. I think I'll start with just basic recursion, and if I'm stuck there, then I'll pre-populate the solution with the brute force ones that we are discussing right now. Sure, I think I'll do that. Okay, let's start with recursion, the basic recursion function. And this would basically be our mpause, which is an end, cat pause. Again, we are given default values for them. So this by default is 1. This by default is 2. And then we finally have move, which is basically whose turn it is. M turn, let's say. Let's just call it turn actually, which if it is 0, then it is cat's turn. If it is 1, then it is mouse's turn. And pass. Okay. Makes sense. Okay. Now, I simply start calculating. I think so. I think it's just easy to just start calculating from here. So for node in, okay, actually base condition. So the problem is key. Basically, the problem is we are just given the graph, right? And within the graph, we are given key how many nodes 0 is connected to. Actually, let me call it 0 nodes, and then that would be helpful. It would be just easier to make a set of all of the lists because we need to quickly check for a few things. I'll tell exactly what I mean. Let me actually remake the graph, and I think it will be helpful. Graph is equals to set row adjacency matrix, I think the bad way, and then adjacency matrix is the bad way, and the adjacency list is what this is called. Row for row in graph. This converts all of them to a set, which helps us because now what we can do is if turn, then we know it's mouse move. If it has mouse move, then we can simply question, hey, if 0 in graph impulse. So if the mouse's position, actually let me call it either C pause, C pause. So if 0 is an impulse, and this now runs in constant time. So if 0 is an impulse, then we have mouse wins. So we simply return 1 because we know for sure that mouse wins here. No matter where the cat is, actually, yeah, we also have no matter whose turn it is, if m pause equals c pause, then cat wins, so return 2. Sure. Now we have if it's mouse's turn, and it is basically 1 away from 0, then mouse wins for sure. And another thing that we can check for is actually I'll do this. I know I might have to change it later. And graph impulse. Similarly, if not turn and impulse in graph cpos. That's why I wanted to make it a set and not just do store zeros, because if the cat can grab mouse in its turn, then it will. So we'll simply return 2. Now these not necessarily are base conditions, and I should also store them in DP so that we don't continuously run this or rerun these calls for no good reason. I think I can store this in DP as well, but sure, let's try it. So I'll store this in DP. DP, let's say we have mpause, cpause, and turn is equals to 1. And in this case, it is 2. And we can also discard it from calculating. So what I'll do is I'll say hash key is equals to, or state is equals to impulse cpause turn, and simply do state. Same here. Actually, in here I will populate it with some conditions, I comma j for I in range len graph, for j in 0 comma 1. I hope this is correct. I hope it gives me exactly what I want. And then again, we do not need to worry about this one. So now we have established the basic win conditions, right? This is kind of what I was going to pre-populate it with, but it wouldn't be difficult. And actually, we also need to do, hey, if we already have this, so if state in, actually we can simply do calculating dot discard, because then if it is not there, do nothing. State. And we can simply run this again here. Hmm. I think there's a lot of same things going on here, so I might refactor it later, but for now, let's just continue. So now we have our basic or kind of base conditions for our recursion. Now we need to move on to actual recursion part. To do that, we will do for node in graph. So whoever's move it is, so let's actually again write it properly, and then we will do if turn. So it's mouse's move. So for row in graph m pause, where can we go? And sorry, not row, node. Uh, if answer is equals to, I will say 0, or let's say -1. Mm, if so, that's kind of where what I was wondering, and that is this is kind of where the only problem with this approach and the only kind of issue happens or arises is which node do we want the answer first. So when we're calculating for this node, do we want the answer first for this node, or does this node's answer depends on this node? We can never know that for sure unless we know how far each node is from 0. Not necessarily, I think. So in the circle problem where we had lot of nodes connected to 0, to get the answer for this particular node, should we wait for the answer for this node because this is closer to 0? No, but this will give mouse the correct answer. So basically in here, what do we do? Do we wait for, if it is already calculating, then do we simply just attach to it as in, mm, so the thing is, if it were, since we are doing recursion, if it were already calculating for a particular node, then we're simply trying to go back in time, in which case we can just ignore its answer and we can simply continue, move on. So here's what I'm thinking. If we were, if we are to reach a state for which we were already calculating the answer for, then we can simply move on. We don't need the answer for that state to evaluate the answer for our current state because that state depends on our current state to get its answer. Say the idea is that we are given an initial position, meaning to get to the answer, asking again the initial position, hey, what is your answer so that I can get my answer is ridiculous at the very least. What I mean is, if this was our initial position, so it's 641 and we arrive at what 630, and then let's say through some miracle we arrive back at 641. This like basically asking 641's answer to calculate 641's answer is ridiculous. Simply we will move on. So if the node, so or if node comma c pause comma 0 in graph in calculating, then we don't care about it. So simply continue. No, if it isn't, then we need the answer for it. So answer is equals to, and if at any point, okay, this answer is equals to recur node comma c pause comma 0, not full. If this answer is sorry, okay. Actually, I think we can simply do answer is this. If answer is ever 1, which means that the mouse wins. Okay, but we can do that. We'll have to have this answer. Reason being, if this answer is 2, sorry, is not 2, then answer is equals to this answer. What am I doing? I'm acting stupidly. So there are 3 possibilities. Answer can be either 0, 1, 2, -1. And for each of them, there are 3 possibilities that this answer can be 0, 1, or 2. That's it. So if this answer is 1, then we know for sure, hey, this answer is like we will return with 1, because again, our turn is it's mouse's turn, so it wants the most optimal thing, and 1 is the most optimal thing for it. So we simply say answer is 1, and then we break. The reason I'm doing this is I want to store these things to DP as well, is equals to answer and then return answer. If this answer was not 1, so if then this answer can be 0. If this answer is 0, actually let's just do if this answer is not 2, so this is the worst possible case for mouse. In this case, if answer was -1, then only set answer as 2, else simply continue. And I don't think we even need to write that. Yeah, otherwise we don't care about it. So actually we can do and answer was -1.